So I'm very pleased to introduce Mike Frank. So Mike got his PhD at MIT and is now associate professor at Stanford. He's an expert on how kids acquire language and how they, interpret it and use it to reason. One of the things, I think, his findings will be very useful for us, but also his experiment design and how he works with young kids. I think it's really interesting to see. So take it away.
Great, thanks. Thank you very much, Jessica, for the invitation. Thanks, everybody, for having me. So I'm going to be presenting on one particular line of work on children's reasoning about communication and context. I chose this to err on the side of coherence, but I understand there are a lot of diverse interests, and I'd love to take questions on any aspect of this work or really anything about children's language development. I figured it'd be more useful for me to present my own work, but then we can kind of veer off into the broader context and the broader kinds of methodological and topical issues that you guys are thinking about as we go. And I'll say now that I'm going to start by presenting some theory and theoretical framework that's supported by work with adults, and then we'll get to kids kind of towards part two. Okay, so here's Hagar the Horrible, and he says to his dim-witted friend, "Any luck?" And his friend goes, "Any luck with what?" And Hagar says, "Any luck with fishing?" His friend says, "Why didn't you say so? I'm not a mind reader, you know." Similarly, Jeremy says, "Can I borrow 10 bucks?" Mom says, "No." "Can I borrow 20 bucks?" "Jeremy, if I wouldn't lend you $10, I'm certainly not going to lend you 20. "Okay, how about 40? Okay, so thank you very much for that laugh. To the extent that these are funny, and I think it's debatable whether they're funny because they show the errors made by two individuals who don't know that language interpretation in a particular context is going to require reasoning about the other person with whom you're communicating. It's going to require inferring their intentions and trying to figure out what they're trying to tell you in this particular context. So people, of course, in thinking about language and how it's used, have been considering this problem for a long time. In particular, the kind of dominant view in thinking about language understanding is that in order for language understanding to really work, you have to proceed from an assumption of cooperativity, that you've got a partner who's trying to tell you something about the world, and they're doing that in as helpful a way as possible. So one view on this is that you think, okay, speakers are assumed to obey a certain set of rules, be relevant, truthful, informative, clear, concise, and so forth. And then if you're a listener, then you get to make inferences about what somebody meant by assuming that speakers followed those rules. This framework is due to a philosopher named Grice. He had a kind of broader viewpoint here, though. So his idea was that you could see talking as a special case of rational behavior. In other words, language use is just like any other kind of action you take to achieve a goal. You say some stuff to try to get a particular thought in somebody's mind, but you can also do some things to try to achieve an end. In both cases, you're going to want to be maximally efficient to do this. So thinking about Grice's framework, he was able to make a set of predictions that explained a lot of seemingly incoherent phenomena about language. So for example, you get this recommendation letter, and the recommender says, "I recommend him for your position." He has really great penmanship. He shows up on time all the time. Hire him. And you, of course, don't want to hire this person. But the reason you don't want to hire him is because you have to assume that the recommender was being maximally informative given the constraint of being truthful. And if they're maximally informative and truthful, then you have to assume that other things they could have said are not the case. They could have said smart, hardworking, creative, and no, that's not going to be what happens here. Or in a much smaller scale, if I tell you that I gave an exam last week and some of the students passed the test, you might infer that the exam is hard. Why? Well, because I could have said that all of the students passed the test. I didn't, and so all of them probably didn't. Some, but not all of them, probably passed. So these kind of inferences, they sound kind of like edge cases, but in fact they're just all over the place in language understanding. From kind of classic examples like "time flies like an arrow," these ambiguities of that sort, all the way through kind of complex discourses that we see in natural situations. Basically, everything in language understanding really requires this kind of reasoning about speakers' intentions in that particular context. Just one thing that makes computer speech recognition, computer speech understanding very, very difficult is that typically the task is decontextualized. So putting contextual information in the mix, even very, very simple pieces of contextual information can dramatically increase performance for automated systems. Okay, in this talk, what I'm going to be doing is formalizing a model of this kind of language understanding and context. And the reason why I think this is important is because typically people have understood that language in context is governed by this kind of rational, goal-directed action, but it doesn't end up formalized into a lot of models. Instead, it ends up in what people have called the pragmatic wastebasket. Pragmatics being all the rest of language that happens in context that's hard to reason about, that's AI complete, it's terrible, so let's ignore it. Let's think about the syntax, the semantics, the phonology, the morphology, but let's not think about pragmatics, this kind of overarching, like, well, people are trying to do stuff. So I'm going to try to give you some tools to think about this question. And I'm going to do this by trying to capture the conflict between two opposing principles, two kind of basic tensions in using language. I want to be informative, I want to tell you about what I want to tell you about, but I also want to save money. And by saving money, I mean not talk a lot, not use hard, long words, not introduce a lot of complexity. These fundamental tensions get summed up in a lot of different ways throughout the history of linguistics, but they're kind of essentially like a fight between trying to get what I want done, but minimizing the burden. And that's when I say rational, that's what I mean by rational, is I want to kind of maximize my utility, tell you stuff without talking all day. And I'll try to do that in this talk with, hopefully some success. So folks in computer science actually had recognized this kind of tension for a long time. Here's two folks who work on generating natural language. They said Grice's maxims taken collectively mean don't include elements that don't do anything. Our position is that under a goal-oriented view of language, you don't need to explicitly follow such a directive at all. This thing just falls out of the mechanism. In other words, try to get the maximal amount done with the minimal amount of money. Okay, so on to an example here. So suppose I tell you that my friend has glasses. Which one of these guys is my friend? Thoughts? Yeah, so you and 77% of people on the internet go for the middle guy. And maybe your reasoning is sort of similar to the kind of folks that we've probed about this, sort of more like that some but not all idea that I was giving you. If you'd wanted to describe the guy on the right, you would have said hat, but you didn't. So it's the guy in the middle who had glasses but not a hat. So that's that same kind of counterfactual reasoning. Well, it would have been more informative to use the word hat if you had been talking about that dude over there on the right, but you weren't, so you couldn't, so you didn't. And so it's not him, it's the guy in the middle. This kind of counterfactual reasoning sounds kind of hard. But it's something we can try to formalize and test. We can ask, do people do this kind of reasoning? And what do they get in these sorts of scenarios? So let me show you now our model for formalizing these kinds of inferences. And this is joint work with my colleague Noah Goodman, who's also at Stanford. We posed a rational speech act model. This is a kind of probabilistic model, uses kind of probabilities as the language for keeping score, keeping track of between alternate hypotheses, and uses Bayesian inference, probabilistic inference, to try to make sense of competing hypotheses. I'll present this in a little bit of detail here, but if you have questions about it, feel free to interrupt me, or we can come back to it at the end. So the fundamental question we're trying to answer here is, for a listener, which referent did the speaker intend given the word glasses? So we're trying to compute what you'd call the posterior probability of a particular referent given the word that was uttered and the context. That's the listener's posterior probability. We're going to use Bayes' rule to factor this into two terms, a likelihood and a prior. So the likelihood we're going to call the speaker's likelihood. That's the probability that some word would have been uttered by the speaker had they been talking about this thing in the context. And then, so that's the speaker likelihood. And then I'll call a reference prior, the probability of a particular face being the referent in this particular context. Do we want to talk about guys with hats and glasses, just glasses, or just nothing at all? So now, how do we get that speaker likelihood? Well, we think about a speaker. This is the speaker's probability of saying a word given the particular reference. So that's where informativeness comes in, because if we're a listener, we're thinking about a speaker who's trying to inform us about which thing to talk about. Okay, but how does the speaker choose? How does the speaker know what's informative? Well, they're going to think about a listener in turn. Okay, so clearly you got a recursion there. This recursion could be endless. Let's ground it out. Let's say speakers don't think about real listeners. They think about kind of fake listeners. We'll call them L0. L0 is what we call a literal listener. Literal listener just says, I'm not going to think about speakers anymore. I'm just going to choose a referent that's consistent with what you said. So if you say glasses, it's one of the guys with glasses, and that's all I know. So the literal listener is the base of the recursion. The speaker thinks about the literal listener, and then the we call it L1, the pragmatic listener, thinks about the speaker thinking about the literal listener. So that's how you get a pragmatic listener who is actually considering what a rational agent would have done to get the job done. And these speakers are rational utility maximizers. I haven't shown you all the mechanics here. They want to be informative relative to the cost. So there's a little bit of relationality with respect to how long the utterance is. So there's some kind of, I think, decently nice math you can do here, which shows that being informative, all else being equal, you can define that as transferring the largest number of bits. And then you get this kind of recursive formulation. So the information theoretic optimal in terms of transferring bits actually kind of boils down into this sort of same probabilistic model, which is kind of fun. Okay, so that's the abstract setup here. Let's apply it to an example, these hats and glasses. Let's actually try to compute these probabilities, which turns out to be remarkably easy. It's sort of a paper and pencil model at this point. Okay, so you could call one of these hat and glasses games here a signaling game. These signaling games have been studied in philosophy and linguistics for many years, going back to David Lewis and others. Just waiting for this guy to click over. So you can think about this guy, this set of three objects, as a matrix of reference or meanings and words that you could say. So, right, the top row is the three objects, and you could say hat about the guy only on the right, and the bottom row is glasses. You could say that about both the guy in the middle and the guy on the right. So now the literal listener defined over that matrix is a set of conditional probabilities. If I say hat, then it has to be the guy with the hat. If I say glasses, then it could be either of the guys with glasses. Now, thinking about a speaker who's considering that literal listener, we can just transpose the matrix and derive those conditional probabilities for a speaker. What should they say if they want to talk about each of these guys? I'm just going to build this full slide so that we don't have to wait. So the informative speaker, thinking about the guy who has a hat, would probably want to say hat rather than glasses, because the literal listener would be most likely to get that guy if you said hat. In contrast with the guy with glasses, you have to say glasses. There's nothing else you can say, and so you get a 1 in that column. So then when we build to the pragmatic listener, then glasses now strongly means guy with glasses as opposed to guy with a hat because of that competition. But the pragmatic listener is thinking about the informative speaker and what that informative speaker would have done. So that's the kind of intuition, and that leads you to then converge on the guy with glasses and not a hat. So, for those of you with an inclination towards these sorts of matrices, you can kind of see that this is actually, you might think of as a matrix whitening scheme. We're taking kind of off-diagonal elements and getting rid of them by this recursion. And the degree to which we get rid of them is, corresponds roughly to the depth of recursion here. So in some game theoretic versions of these sorts of models, what you do is you iterate until you find a fixed point in the matrix where all the kind of quote off diagonals, doesn't have to actually be a diagonal, but all of the non-equilibrium points get whitened out. They go to 0. And so those are the fixed point solutions for these signaling games, but they're actually, humans don't tend to go all the way to the fixed point. They tend to have some probabilities. Okay. So that's the basic model. Of course, there is a prior in here that we would use. I've left it out for to simplify the example here. Okay, so in context, these rational speech act models are a special class of probabilistic models in which you do nested inference. It's not just inference in a standard probabilistic model, you actually have to reason about somebody else who's reasoning about somebody else. This framework provides a way of applying pragmatics to arbitrary signaling systems. But in order to do it over an arbitrary signaling system, you have to give me both a syntax and a semantics. So that would be hard computationally in a really big system, but it's trivial, as you've seen here, in a very easy system. We have some kind of fun approximations, which if you're interested in, I can talk to you about. You can do this using kind of neural net style models that are trained with this sort of recursive pragmatic input. Sorry, I'm kind of talking forward for the slides because it's taking about a minute to switch over. These are related to game theoretic models that allow you to study equilibrium behavior. So the goal here is these guide your intuitions, and they become a tool for describing empirical data. So that's the framework. And within that framework, the central argument I want to make today is that pragmatic reasoning and language comprehension can be described by these sorts of rational goal inference models. Okay, so the outline here is that I'm going to show you some initial tests of this model, then give you some evidence about kids' pragmatic reasoning and their word learning, which I think was inspired by and really captured fairly well by this kind of model. And then, if we get a little chance at the end, I'll tell you about some ways that this kind of pragmatic reasoning actually informs the structure of languages. There's some Google data in there, which is fun. Okay, so this is the first experiment that we did to study this kind of stuff. We stripped things down even further than the hats and glasses. We told speakers, imagine you're talking to somebody and you want to refer to the middle object. Would you say blue or circle? And this is a less nice but isomorphic matrix, or representation of the same matrix. So if you wanted to talk about the middle object, you should probably say circle, because circle is a unique descriptor of it. So then if a listener is thinking about this and somebody uses the word blue, then it should be the square, because if you had been talking about the circle, it would have been blue. The speaker then was asked to do this across a number of different conditions. Some cases where there was kind of one blue thing and or one circle and two blue things, one circle and three blue things, two circles and three blue things, and so forth, kind of throughout all of these. And of course, I won't mention this, but in all these experiments, we don't just do the experiment with blue and circle. Everything is randomized. There's also pink stuff and triangles and so forth and so on. And this is done with 300 people on Mechanical Turk, on Amazon's crowdsourcing marketplace. So we did these experiments trying to kind of strip out everything that would matter and average across lots and lots of participant judgments. And what we see is the more, the greater the ratio of blue things to circles, or vice versa, the stronger the judgment that you should say circle relative to blue. So the kind of informativeness of one predicate over the other increases the speaker's judgment. And here we used a measure where we asked people to bet. They had $100 and they'd bet whether a speaker should say blue or circle, or square or blue or whatever. That produces graded judgments. You can reproduce the same finding by just asking them to choose which one they would say. It doesn't really matter. In this case, we used the static measure. Okay, so now we want to compute the listener condition. So there's a problem with computing that because, as I mentioned to you, there's a prior distribution that we need to take into account. People talk about different things, different amounts. So we got at that by actually asking people to comprehend what a speaker said, but then not telling them what the speaker said. We said the speaker has one word to tell you about this display, and they say mumble, mumble, mumble. Oh, you didn't hear what they said. Which one do you think they were talking about? So that's literally the definition of a prior distribution, right? We tried to query their distribution without giving them any data to change their distribution. And what we get is, as you might expect, people don't talk about stuff that's as much that's kind of not unique. So the blue square here shares a feature with the blue circle and with the green square, and so it gets a lower ranking in terms of whether people think the speaker would have talked about it. So we take that empirically measured prior distribution, we multiply it by the model prediction for informative uses of the predicate blue, And what we get is a pretty good fit to listeners' judgments. In some sense, what we're trying to do is connect a bunch of different measurements from people. We could even sub in the speaker data that I showed you. And we're sort of using the model to compute the relationship between the prior elicitation task, the speaker task, and the listener task. We get pretty good fit to this particular case where it turns out that the prior distribution actually cancels out the inference about the informative use of blue. They kind of work against one another, and you get a pattern that kind of is relatively flat. But across a lot of examples, we get a very nice fit to the empirical data. So there's really a kind of nice correspondence between the model predictions and this first test, at least in these very restricted cases. And I stress that the reason why this works so well is because we randomized out every other possible factor that could have affected these results. So this is a little bit of experimental trickery. We just made sure that we counterbalanced or randomized all the stuff that people care about except for the pragmatic arrangement in the context. This is a kind of first proof of concept which showed a nice correspondence to the data. But we kind of didn't really deal with a bunch of the issues in this model. We set the level of recursion artificially, we measured the prior, and we experimentally controlled the speaker costs. So we've done a number of follow-ups to this study, testing parts of the model independently. I'll mention those briefly because I think it's important to understand that these parameters can be brought under experimental control before you go on and try to test more exotic things. Okay, so first, we looked at whether people could actually do deeply recursive reasoning. So this is the same kind of result I was showing you before. These are data from the hats and glasses now. So you can see in green here, I've boxed the hat. So hat is what you'd call a level 0 inference because that's just the meaning of the word hat. You don't have to think about anybody to figure that out. Then I boxed in blue the glasses because that's a level 1 inference. You need to do one recursive cycle in order to figure that out. The human performance is 75% for the level 1. Now here's a matrix that's a little more complicated. There's actually a level 2 inference. So we've got hat still gets you hat, glasses is hard, mustache is sort of like the glasses was, but glasses, if I say glasses, well, there are two guys with glasses, and each of them have another thing. In order to figure out the glasses one, you need to say, oh, well, if you'd wanted the guy in the middle, you would have said mustache, and you didn't, if you wanted the guy on the left, you would have said hat, and you didn't say that either, and so glasses must refer to this guy on the right. And that's a much harder inference for people to make. We're still working out exactly why people strike out on this and whether under some circumstances they can get it. We think maybe we can kind of scaffold them into it, but this feels a little bit more like Sherlock Holmes than like language comprehension in context. So recursion appears to be limited to kind of 1 or max kind of 1.5 levels in practice, at least in these simple experiments. Second thing I want to show you here is this issue of the prior. So as I mentioned, what I did in the previous experiment was measure the prior empirically. But that's actually, technically that's a correlational measure. That's not actually establishing any kind of causality. I just measured one thing about people and measured another thing about people and showed that they correlated with one another. Used them to correlate with a third thing. What I actually want to do is manipulate the prior and show that that affects human behavior via the route that I care about. So just reminding you of the formulation here, the listener is a function of the speaker times the prior. So that's the thing that we measured but didn't manipulate. So here we manipulate it by just telling people about an interlocutor named Bob. Bob visits a friend every week, and here's the friend that he visits for the last 9 weeks. Okay, so that gives you an empirical prior distribution. And now we do the same 2 measurements. We both check on the prior, and then we also do the my friend has glasses thing. And what we find is that if you plug that measured prior into the model, you get a good prediction of the listener's inference, and the listener's inference is changed by the strength of the prior. So it just shows us that we can actually push around people's judgments by manipulating this term of the model, which is a nice piece of evidence for it. Okay. So we've got graded sensitivity. So okay, now that puts us in a place where we've got this theoretical framework. It shows some fit to adults' data. now we can actually start to apply this to the situation that I'm primarily interested in my own work, which is children's pragmatic reasoning and their word learning, how these two things go together. Because a little bit of background on word learning, probably the primary finding in word learning, in some sense, is how deeply grounded in the pragmatic context it is. So word learning is very, very much enmeshed in social interactions with caregivers. It's hard, as Jessica and I were just talking about, hard to learn from kind of static, passive viewing of media. It's much easier to learn when you have somebody who's giving you this rich set of interactive social cues, saying, "This is, a pen. Have you seen a pen before? Look at this." We capture the listener child's attention. Elaborate. Oh, you see the cap? It goes on and off. This kind of classic parent talk is designed to capture attention, bring it to a referent, elaborate, provide repetitions, kind of narrow the world of hypotheses that the child considers. So that's all well and good. But then when you think about pragmatics in language learning, kids are actually terrible at pragmatics, right? They can't lie. They constantly say decontextualized things. They'll run up to you and be like, it broke, it broke, it broke. And you're like, hold on, stop, slow down. What broke? You're not thinking about what I know here. You're just talking, right? So there's this kind of fun puzzle where kids learn a lot from social contextualized language use, but they also strike out in some interesting and thought-provoking ways. So we've been using this model to try to get a handle on that kind of mismatch. So let me show you first just a really, really simple demonstration that this basic phenomenon is present in kids. So I'm going to mute my, I'm going to unmute my computer and mute the video here.
I'm going to mute here, us then.
Great. Okay. Are you muted, do you think?
The other laptop is picking up the other group. At least one person be seated right. Did anybody be seated?
I see. Yeah. Okay. We're getting feedback from abroad. There's a dragon.
You're on
How would you describe the dragon?
Oh yeah, this is great. Natural experiment. There's a large reference set.
I'm going to unmute for a second.
Okay.
Please mute on VC.
Okay. There we go. All right, I'm unmuted and safe now. Nope. Okay. I'll play this video without sound. So here's a child in one of these experiments. There's a puppet interlocutor who's very dumb. You have to help him find his friend, his house, his car, his plate of pasta.
So we can't hear the sound.
Unless
I should be on.
My friend has a hat. Can you show me my friend?
there we go.
Awesome.
So we've got this puppet interlocutor here.
Oh. Or do you want to play it again?
Nope. There we go. And the puppet, you have to help guide him through his day, help him find his friends, help him find his glasses, help him find his, his car, and so forth. And then we ask kids to make judgments within this set based on this puppet's underinformative utterance, glasses. That gives a cover story for why the puppet would be saying such silly stuff. And what we find is that the rate of choosing glasses, the one feature option, goes up from age 2 to age 4, 4.5. We start to see it pull apart from the responses to hat and glasses, really by 3 or maybe 3.5. So this seems like not that hard a task, but it stands in striking contrast to the kinds of failures that people have seen with kids before in these sorts of tasks. So for example, if you show kids 3 horses and all 3 jump over this fence, then you say, some of the horses jumped over the fence, they're like, okay, that's totally fine. That's not underinformative at all. Which is, of course, different from what an adult would say. That so the adults say that that's a terrible sentence to describe 3 out of 3 horses jumping over the fence. So there's this real mismatch, and that's 5-year-olds, maybe even 6-year-olds have problems with the some of the horses jumped over the fence task. Yet 3, 3.5-year-olds are doing okay on this particular hat and glasses task. So this suggests some kind of earlier pragmatic reasoning than we would have expected, kind of congruent with this basic framework where social pragmatics early on is helpful in language learning. It also provides a tiny little clue, and some follow-up data sets kind of support that, about what's going wrong with the 2-year-olds. You see there's actually kind of a crossover there. It's pretty small in this data set, but it's bigger in some others where we use eye tracking. They actually, they choose the guy with the hat and glasses more, because hats and glasses together are cooler than just glasses. So this is kind of an important signal for us of what's challenging for kids in these sorts of situations. In particular, the thing that's challenging for the kids is tearing themselves away from the prior, from the thing that's cooler, because they have a lot of trouble at this age with inhibiting what you call a prepotent response, a response to the kind of coolest thing, the sort of most natural thing to respond to. So it's not that they can't make the inference here, we'd argue. We're starting to get some evidence to support that. It's that the inference is blocked by the cooler thing that would otherwise attract their attention. Okay, so the kids can make this sort of inference. Let me show you a case where this inference actually then helps them learn a word. So imagine I show you these 2 dinosaurs, and I point to this guy on the right in sort of a non-specific way, and I say, this is a dinosaur with a dax. Now, what do you think a dax is? Thank you. Great. Good plan to the audience here. So when I ask you this test question, which of these has a dax, you would then answer the guy on the right. Has a scarf, as opposed to the guy on the left who has what I've now learned is called the fascinator. English royalty wear these. So in the language of these kind of ratios, we would call this a 1-2 trial. This is the display there is flipped, but it doesn't really matter what the feature is. It matters how many of each feature there is. So there's 1 fascinator there and 2 bandanas. So if I point to the guy with the fascinator and the bandana, you'll think it's the fascinator in that case. I could do it where there are 3 bandanas, and then really, why would you be talking about a bandana? You should be talking about the fascinator. And adult judgments about what DAX means track really nicely with that. So you get this very nice quantitative relationship between the ratio of bandanas to fascinators on the one hand and the average support for DAX being the kind of more unique thing. But more importantly, we can look at kids. These are 3-year-olds and 4-year-olds. Again, I'm plotting the kind of portion correct. There are 2 types of trials here. There's filler trials and inference trials. Inference trials are what I'm showing on the left. Filler trials are the same thing, except the guy who I point to doesn't even have a fascinator. It's just completely unambiguous. All you have to do is remember what I said. And what you can see, the thing that I found striking in this, is that actually the filler trials are not that easy for 3-year-olds, because you have to remember a lot of bandanas and fascinators and stuff across the experiment. And the inferences are basically no worse. They're like only a tiny bit worse. So what this shows is that 3- and 4-year-olds are actually able to use this kind of inference to infer the meaning of a word. I also think this is consistent with that sort of salience explanation I was giving, because here the 3-year-olds are pretty good, by 3-year-old standards at least. And what you see further is that in this case, the guy who I'm pointing to is actually cooler than the other guy. So there's no conflict between salience and informativeness here. The guy who I'm pointing to, by virtue of this task design, actually provides the kind of best thing to look at, and I'm pointing to him. So there's no conflict, and the 3-year-olds are winning. So that's kind of another little piece of evidence suggesting that it really is this tension between, okay, it's hard to rip myself away from something awesome, minorly more awesome. They're not, these stimuli aren't that awesome. It's hard to rip yourself away from something awesome to focus in on something that's kind of informative or useful. Okay, so here's one more experiment that suggests that this kind of pragmatic reasoning actually can be a very powerful way not just to learn words, but to learn about the world. So this is the work of Ali Horowitz, who's a grad student in my lab. So suppose Ali says to a kid, this is a broken tibu. Okay, what do you think tibus usually look like? So hopefully you agree that they are more likely to look like the thing on the left than the thing on the right. But suppose I had told you it was a small tibu instead. Then maybe you generalize to the thing on the right. So what you can see here is the inference that we're testing is that because I used a word contrastively, that is to be informative about the thing relative to some context, you can now infer what that implied context is, what tibus usually look like. And you can see this sort of inference all over the place in the real world, both in positive contexts, like maybe I say, hey, let's go to the art museum, and you're like, oh, there are other types of museums? Wonder what those museums show. So you're kind of learning by my contrastive use of a modifier what the world is like. Or you can see that in very negative contexts, like gender stereotypes. Like I say, oh, I went to see the male librarian. They're like, why are you saying male librarian? Either there is some expectation in the world, or at least you have that expectation that there's some gender differential there that you need to, kind of work around. So this kind of implicit learning from the implied contrast set then becomes a mechanism for you to get all these kind of social expectations that are out there, as well as knowledge about categories. And what we find is, again, that 3-year-olds are able to do this kind of inference, and by 4, 4.5, they're really kind of getting up to adult levels here. The two different bars here are the broken versus small. So broken we called feature. These are these opposite features, and size is the small, large kind of features. So let's provide some evidence taken in sum that children make pragmatic inferences earlier than previously supposed. And they can use these inferences to learn about words and to learn about the world more generally. Okay, so I'm close to the end, but I want to spend just a few more minutes telling you about some cool new work that we're doing on how this kind of pragmatic reasoning can lead to language change. So there's a little bit of extra theory that I need to inject here. So the basic model that I described does a lot of pragmatic work, but it doesn't do all of the pragmatic work that we need. In particular, here's an inference that it can't account for. So this is a classic example. I say, John got the car to stop. And you're like, oh, what happened? Because he didn't use the brakes. Maybe the brakes were not broken. You had to use the emergency brake. Why do we get that inference? Well, the kind of idea here is that John got the car to stop is a weird way of saying John stopped the car. The weirder the thing is, the more likely it maps onto a weird kind of outcome in the world. A low frequency way of saying something maps onto a low frequency way of talking about the world, or state of the world. These are called by convention, because of this guy Larry Horn, who's a linguist who described them, Horn implicatures. And reasoning about them actually requires uncertainty about the lexicon for some kind of technical reasons that I won't go into. But you have to set up the pragmatic model to say the listener is actually reasoning about the speakers in a world where they're not totally sure what all the words mean. Basically, they consider the possibility that got the car to stop means just this kind of special case, or it could reply to kind of the broader set of cases, and they kind of average across those. It's a way of breaking the symmetry between these two statements, got the car to stop and stop the car, which actually mean the same thing. So they consider a world in which they don't mean the same thing, and in that world where they don't mean the same thing, it's actually kind of cheaper and better to have it work that way. And that breaks the symmetry and allows the kind of pragmatics to go forward as usual. This is sort of has been a little complicated, and so I'm happy to talk a little bit more about that. But for my purposes, actually, the kind of model that averages across what words mean, that's actually precisely what I was talking to you about with kids, right? That's a model of language learning under pragmatics that doesn't know what words mean and figures them out. So that's kind of fairly familiar territory. Skipping forward, this kind of model that doesn't know what words mean actually allow for the emergence of lexicons. So if you can kind of have a model that does pragmatics while sort of learning words, you can actually kind of figure out what words mean in a context where you don't know anything. You could talk to somebody that you have nothing in common with and figure out a kind of signaling system that works for you. So this is a simple simulation from a paper we wrote about this, where you can see the kind of two agents trying to converge on a signaling system. And here they converge on sort of one signaling system. Here they converge on a kind of potentially a different one. You can kind of just make up a sort of diagonal along this matrix and go with it. It doesn't really matter which one it is. And you can kind of see that the probability of understanding in these sorts of very, very simple iterated games where you just signal at each other and then try to learn from that actually kind of works pretty well. And there's sort of a bunch of psycholinguistic findings that are related to this, where you put people in situations where they really have to like make weird symbols to each other and they figure out how to use those to play games together. But okay, so this kind of emergence finding allows us to study these kinds of horn implicatures, these implicatures where the kind of length of a statement actually maps onto its complexity or its unusualness, this got the car to stop type of thing. And what we find in this theoretical model is that these horn implicatures actually get lexicalized. You end up learning that the longer statement actually means the sort of more unusual meaning. So you actually sort of fossilize that into the lexicon, which makes a kind of fun prediction that we have been testing, which is that in natural languages, more complex meanings should map to longer words in general.
In the previous thing where you said good lexicon and bad lexicon, what is good and what's bad?
So a bad, this is I'm sort of skipping over the simulation just to get to the data here. The good lexicon is one where got the car to stop, the sort of longer expression maps to the more infrequent meaning. So this is a, so the simulation here is about how often the models learn that's actually what the word means. So the good lexicon is one that's set up where the long expression maps to the unusual meaning. Bad lexicon is one that's vice versa, where the long expression maps to a usual meaning. And that mapping doesn't get learned because it's just too weird. Okay. It violates the pragmatics, and so the models don't encode it as part of their kind of state for the lexicon. Whereas if you do have this kind of asymmetry where the long expression goes with the more complex or more unusual meaning, then those things get fossilized in and become part of the actual lexicon. Sorry about that. So we tested the prediction, this kind of prediction that you'd get lexicalized horn implicatures, which is kind of a complicated way of saying long words should be more conceptually complex. So our strategy was we asked people how complicated the meanings of particular words were. We took a sample of 500 words that have been studied by other folks, and we just compare these word meaning ratings in terms of complexity to word length across languages. So two things to say here methodologically. One is that these complexity ratings, that's like a very weird task to be like, Brick, what's the conceptual complexity of this meaning? Yet people give really consistent answers on this kind of task. You can ask two totally different groups of people and you'll get very, very similar ratings. We have some intuition about complexity, which I'll get to in a moment. Okay, where do we get word lengths across languages? Well, you guys nicely provide us with Google Translate, which allows us to look at 83 odd languages. This is the correlation between lengths of those 500 words, 499 words, in each of those 80 odd languages, and their conceptual complexity.
So English has the longest words?
Sorry, no, English has the highest correlation between complexity and length. And that's probably because it was English speakers that came up with the complexities. Right. Yeah. But okay, a bunch of things to notice about this complicated plot. First thing first, they're all above 0. For all 83 of the languages, it's above 0. So that the mean is about 0.3. It's lower than it is in English, but bigger than it is. By chance, you would not expect these correlations. Second thing to notice here, there's some pink bars, some red bars. Pink bars are Google Translate. Red bars are hand-checked languages, so we went back and checked the translations. Turns out Translate did quite well. It was like, high 80s, low 90s for all of the 12 languages that we had linguists check for. So didn't make any difference to the correlations. Third thing here is length is also correlated with word frequency, and that's a big confound to the study. So those triangles actually show the decrease in the correlation when you partial out the word frequency. And it actually doesn't do all that much. I mean, it does something very reliably across languages, but the relationship is still overall very positive.
And you said all of these ratings are done by English speakers.
Yeah, so all the meaning ratings are done by English speakers. We're in the process of trying to get meaning ratings by non-English speakers.
And you determine length by number of letters?
Orthographically in this study. In English, yeah, so number of letters. In English, you can do it with number of phonemes or number of syllables. These are, of course, very highly correlated. Phonemes actually does better. That's the more kind of psychological measure, and so you'd expect it to do better. We just don't have kind of accurate phoneme dictionaries for any of these other languages. Otherwise, we would do that. But yeah, when you can do phonemes in English, it works much better. Sorry, I shouldn't say much. It works substantially better. Okay, so this is, kind of. Oh, go ahead.
Chinese and Japanese are very, very far apart, even though they use a lot of the same characters.
Yeah, that's true. I'm not a speaker of either of those languages, so I can't check that. But my intuition would be that a bunch of these words are like kind of, they're relatively abstract. Not all of them, but a number of them, and so they may actually have different forms in Chinese and Japanese.
Japanese slips everything into like 2 or 3 kanji.
Not always.
Not-
So Japanese also has an actual alphabet that they
Right.
go by versus Chinese that typically sticks to kanji.
But it depends. But Google Translate doesn't do that very well.
Right, the Romanji, yeah. So I would have to check exactly what's going on here, but my guess, I know that vocabulary and character overlaps are greater for kind of historically older words, and I suspect there's a good chunk of our words that are not historically older, and so there's less form meaning alignment there. Most languages.
Is it also dependent on the language? Like the words that you pick from English don't really map to the other languages as being the most frequent words, or?
Good question. So word frequency distributions do align decently well across languages. So this is the same set of 500 words, which were in part chosen because we thought that they had some chance of translating across languages. Right now we're using English word frequencies because of that correlation. We're using English word frequencies as a proxy here. So an ideal version of this study would be that we got complexity ratings in all of the 83 languages and then word frequency distributions in all of the 83 languages. That would be awesome, but corpus resources and crowdsourcing or participant resources don't exist for the vast majority of these. So I think what we're going to end up with in the end is a couple of languages where we check, okay, in this language we have frequency distributions and it looks the same. Yeah. So this suggests that some of this structure is kind of fossilized into languages. But I haven't actually shown you that kind of individuals make this sort of inference in the moment that longer words map to more complex meanings. Let me show you that now. We've got to bring things back into the land of weird words and odd objects. So imagine you just heard somebody say Fepopolis, Fepalopus, I guess. I haven't pronounced that one. Or which object do you think Fepalopus refers to? So we ask people for this judgment. It's not as strong a judgment by any means as many of the others, but these objects vary in their complexity. In fact, what we've done here is created a set of objects that have 1, 2, 3, 4, or 5 shapes, and then we compare 1 versus 5 shapes, 1 versus 4 shapes, 1 versus 3, and so forth, all the way on down at all ratios. That gives us a complexity ratio, and we're plotting that on the horizontal axis. On the vertical axis, we get what you call linguistic complexity bias. That's the effect size of the bias to map a longer label onto the more complex thing.
And does that also correlate with the type of shape?
In this particular study, we randomized everything like crazy, so we don't have any of that. I would guess that kind of more unusual shapes would end up with longer labels, as well as.
I mean, because in other studies they've found that certain word sounds associate with round shapes.
Yeah, that's right. So there's that. Yeah, that's a great point. So there's this kind of boba kiki. Bobas are round and bulbous, and kikis are sharp and spiky. That effect should be independent here because we're kind of randomly generating these nonce words with the same structure, and we're kind of randomly concatenating the shapes, the geons. We've also done the same study, just sort of maybe getting at that point in a different way, with this set of natural images. These weird images that we found on the internet somewhere that we didn't have a name for. We asked people on the internet again to rate these images on their complexity, and they're ranked. There's sort of an ordering there from this kind of weird dog bowl-y kind of thing on the upper left to this very odd sort of like weird shoe-based letterpress thing on the lower right. There's this kind of complexity gradient. And when we use that complexity gradient to do the same kind of task, we get exactly the same kind of thing. There's a relationship between the complexity ratings and the words. So, okay, so the kind of upshot here is that these horn implicatures, these cost implicatures, may be a pragmatic force that actually shapes the emergence of natural languages. So you get this, dynamic where even young children are making these sorts of pragmatic inferences that we're describing here, and the fact that children and adults are making these inferences then kind of feeds back into the structure of the actual language that they're using to begin with. So I've shown you a couple of applications of Rational Speech Act models. I'll just mention that there are many others that I didn't talk about today. I didn't talk more than just giving the example about quantifiers like sum and all, but my evil nemesis, Michal Franke, has done some very nice studies on quantifier meanings. There's also some great work from Noah Goodman's lab on non-literal language use, looking at exaggeration and hyperbole, looking at metaphors and so forth. They had a very nice paper last year on hyperbolic use of numbers. This watch cost me $1,000. Did it actually cost $1,000, or am I just mad about how much it cost? Noah also has done some work on epistemic inferences. Like if I say some of the students passed the test, but I haven't finished grading the papers, then you shouldn't that shouldn't imply that all of them didn't. I've done some simulations on scaling these kinds of communication models to multi-listener states, where you actually are thinking about teaching a group of people, and you can derive things like class size effects and kind of tracking or ability grouping effects in teaching from these sorts of models. It's a direction I've been going on recently and I'm pretty excited about. And Chris Potts and a number of collaborators and I have done some work on what are known as embedded implicatures, these complex syntactically based implicatures that linguists have cared about. Like some of the basketball players hit all of their shots. Well, does that mean the others hit, not all, or you can kind of draw out the implicature across the different parses of the syntactic frame. So that's a kind of fun case study. Okay, so in sum, what I've provided you with here is a probabilistic goal inference framework for pragmatic reasoning that makes quantitative predictions about speakers, listeners, and learners, and it allows us at least to start rethinking pragmatic inference in development. So thanks again for having me.
A couple of minutes to lunch. Any other questions?
By the way, if you're using Google Translate, Japanese, it might use hiragana or katakana for a lot of modern or borrowed words instead of the kanji.
Thanks. I will have to take a look at how that was done here. There was some attempt to kind of normalize, because occasionally Translate will actually spit out the English version, because of parallel corpora or whatever, and so we did try to filter those from all of the languages we used. I don't know what we did in terms of Japanese, so I'd have to check. But thanks.
So do you find any results from training, or, I mean, like mathematicians are trained, some does not mean not all.
Yeah.
There exists. So do you have any of those issues with older kids or adults, depending on what kind of background they have?
It's really interesting. I think this kind of reasoning is our default when we use language, and I think that's actually what makes some kinds of formal training really, really difficult. So the reason you have to go to 3 years of law school, the best law schools don't even teach you the law. They teach you how to reason about the law, and what they're really trying to do, in my view, at least part of the time, is trying to talk you out of being a pragmatic listener. The same thing is true for kind of first-year logic courses, where they're trying to talk you out of applying your natural language quantifiers to these cases where they're clearly inappropriate. We actually studied a corpus of people learning kind of logic problems to try to get at that, look at sort of developmental effects as they learn logic. The problem is that really you don't actually talk people out of using natural language in these logic courses. You teach them a set of rules by which they can kind of translate natural language. If this problem says if and only if, then you just got to go with biconditional. You can't go with the conditional. If it's got an if or a otherwise or whatever, you do this other translation. And what you see in their mistakes is that they misapply the translation, not that they're kind of just overly pragmatic. So I think that your point is really well taken, that formal training is about trying to overcome this sort of work, but it's actually very hard. So it doesn't contaminate our results because most people can't overcome the sort of desire to use language in this way.
Does the age at which kids learn proper context and inference vary by language?
That's a really great question and something that I'd love to get at. If you think about the logic of kind of causal inference, cross-linguistic studies are terribly hard to do and interpret, right? Because you can never randomly assign kids to, learn Indonesian, which is a language with very limited kind of morphological and syntactic marking, and so in which you'd expect to see much more pragmatic skill manifesting itself. But say I run that study and I don't find more pragmatic skill, maybe it's that the Indonesian kids were, would have had they been matched for vocabulary or kind of educational experience, but they weren't. Or maybe they are more pragmatic, but I can't conclude anything because maybe they just had more practice with that thing. They're just not it's not a random sampling. This is like the problem of all bilingualism research, that bilinguals and non-bilinguals differ in like a gazillion ways, most of which have to do with their bilingualism, but aren't their bilingualism per se. They grow up in bilingual and bicultural families. They have different family structures. They have different, socioeconomic status. In all of these ways, you can control for those in a regression, but that's not going to do the work for you. So I really want to do that study, and I've been trying to figure out what the natural experiment is, what the setup is that's going to let me do it. So if you have ideas, let me know. That's a key prediction.